All right. Hello, everyone. Any questions before we proceed? Any question from the homework? I strongly urge you to do the homework, very, very much so, because you're not going to learn the material otherwise. Okay. All right. So if you have questions, please put them on the chat. And I'm going to start by a little bit. The question that a lot of you messed up on the quiz was the problem about solving. So I'm going to do this problem again on the board for us, and hopefully you get it going and you don't do those mistakes anymore. So as I do it, I'll walk you through the steps, and I do have the solution on Brightspace, but I want to make sure every one of you get how to solve correctly. So whenever you have to solve a system, basically you have to find the value of x1, x2, x3, x4 that solve the system. And not only one value, we have to find every possible value. That's really what solving is for us right now. So the first approach is always, so step one is to take the augmented matrix and reduce it. So that was -3, 6, 2, 1, 5. I will try a pencil in case I did any mistake. So it's a 1. It's a -2, it's a 1, it's a 3, and a 5. Okay, and then we reduce it. Now, a note about reduction. A lot of you multiplied the first row by a third and added to the first one, to the second one, which is correct. But you know, we want the math to be easier. So if I am doing this problem, I like to have 1 as a leading because the math will be easier. So it means I would start switching rows. Okay, switching is absolutely the way to go at the beginning. And this would give me the following. 1, -2, -1, 3, 5, and -3, 6, 2, 1, and 5. Okay, now what's the benefit of doing that? This is my leading. So instead of having to deal with fraction, I don't have really to do that. So now I take the first row, times it by 3, add it to the second, and this should give me my new second row. Let's realize no fraction in the picture anymore. And those we do them by hand, we try to simplify them. So we do that, we get 3 minus 3, it's a 0. Then we'll have -6 plus 6, it's a 0. And then you have -3 plus 2, which is a -1. And then we will have 9 plus 1, which is a 10. And then I will have a 20 right there. Okay, so as you realize, that is, it's much simpler. Now at this stage, I am in echelon form. I can actually stop. Or we can go to the reduced, but I will talk about that at the end because most of you stopped at this stage, so I will stop at this stage. So now what do we do after that? Once the step 2 is the following, and this I want to make it very clear. What's the step 2? And that's the solutions that you have on Brightspace. You write the system that correspond to the echelon form of the augmented matrix. You identify the basic and the free. And what are the free variables? The free are the variable that correspond to the column with no leading. So step number 2. You write the systems that correspond to that. At the same time, you identify the basic and you identify the leading. Okay, so let's do step number 2 here. Immediately, the basic and the free and the system. The free are the variable that correspond to the column without leading, not with leading, without. So here is the x2 and the x4. The basic are the other ones, x1 and x1 here and x3. Okay, and I write the system that correspond to that. So I'm writing the system. But still I am not solving. Solving, it means we should be able to read the solution. We should be able to look at it and see, find solution immediately. And this is minus x3 plus 10x4 equal to 20. I identified my variable and then I write the system. We're not solving yet. This is still getting there. Now the step 3, that's the important one. We use back substitution. Now we have a system. We use back substitution to express basic variables in terms of free variables only. So we're going to use back substitution. Every basic, in my case, the basic are x1 and x3. I have to express them in terms of the free. I don't touch the free. I express the basic in terms of that. All right, so we will do that. So the third step is the following. And to be able to do this, I have to use those two equations. So those two equations will allow me to express. So let us use this. So the way we write them is x1, x2. Watch carefully how I write the solutions. Now this is free. I write next to it free. This is free. I write next to it free. And now I'm going to use the system that correspond to the echelon form, to be able to express the basic in terms of the free. Now, this one right there will give me, there is a minus x3, so we have to be careful. So it means x3 is 10x4 minus 20. So x3 is going to be 10x4 minus 20. x1, I use the first equation, that's the back substitution. I'm going to use the first equation to get it. So x1 would be 5 plus 2x2 plus, now it's plus x3, but x3 is not free. So instead of x3, I have to substitute x3 by its expression in terms of the free variable. So instead of x3 here, I need to put 10x4 minus 20. Crucial. And once I do that, plus 3x4. And now I simplify that. So this would give me minus 15 seems, plus 2x2, and plus 7x4. That's my
question.
Please ask question.
So you had to start with x3 before you could go to x1, right?
Yes.
Okay.
Yeah, we do, but because there is an x3 in here.
Right.
But the first equation have an x3 in it. There is no way out. Unless you go to the reduced echelon form, which I will talk about it after that. Okay, so this equation does not have only free variable. It has two basics. And the idea is you have to substitute everything in terms of the free variable. So you need x3 to be able to do that. That's why you need the back substitution. With me?
Yeah.
Okay. So now, that's it. So now I rewrite my system just because I want to show you how the solution should show up. The solution should be like this: x1, x2, x3, x4. This free, it means you can associate to this any value you want. This, you can give it any value you want. x3 is you totally constrained by the value you give x4. x1 totally constrained by the values you give x2 and x4. That's what we mean by solving. That's what we mean. You want every possible solution of the system, okay? So you will be tested on that quiz on this next time, which is not next Wednesday. And I have to make sure that all of you have this down packed, right? Now, if instead of stopping at the echelon form, if I kept going, and I can because row operations do not alter the solution of the system, and I can do that, then what would be the scenario? So I will do one more step here. So suppose I go, so we're done, but let us say I went a step further and went to the reduced. What will be the benefit of that? What will be the benefits? To go to the reduced, now I'm going to write this as a 1, and that's a -10 and -20. That's to make things a bit easier. And this will give me -2. And let's see, what do I need? I need minus the second row plus the, so this is, I want to make this into a 0 into the R1. So I will have minus 1 plus 1, that's a 0. Then we'll have -10 plus 3, that's a 7. -20 plus 5, that's the 50. Okay. Now that's in reduced echelon form. And now I repeat the same steps as before. I mean, nothing really changed. So nothing really changed. So now let us do that. Immediately I identify the three, which are this one, that one, nothing really changed. So that's the X2 and X4, nothing is changing. The basic are the other two. Okay, and then now we're solving. So I need to write the system. So I'm doing exactly the same step. So X1 minus 2X2 plus 7X3 equal to 15. Watch, in this case, there is no basic. The only basic here is X1. X3 is not showing up anymore. And the second one would become X3 minus 10, X4 equal minus 20. That's not solving. Solving is this. Some students are correcting me here. I trust them. Very good. All right. Now, solving means the following. Let's see how we're going to solve. All right. Again, X1, X2, X3, X4. The same picture. Free, free. Now I use this equation to express X3 in terms of my free variable. This would give me minus 20 plus 10 X4. Okay, I use the first to solve for X1. The benefit is I will not have a back substitution because the X3 coefficient of X3, which is the basic one, was made into a 0. So this is going to happen equal to 2X2 plus 7X3 plus 7 plus 15, and I think this should have been a minus 15, right? Yeah, this should be minus 15. Yeah, so minus 15, end of the problem. Okay, and we should get absolutely the same answer regardless what you do. Where to stop, echelon of reduced echelon form, it's really a matter of judgment. So you judge, you see, should I go a step further, go to the reduce, or it's easy to do it at this stage. All right, so please go over that. As I said, you will be tested again on them just because I want to make sure everybody can do them very easily. Okay, any questions before I proceed? And the solution is on bright space with all the explanation that I did right now. Okay, any questions? All right. Today we're going to move on to section 3. That means chapter 1, section 1.3. And this is called vector equation. Okay, so before I start vector equation, I have to remind you, I want to use like 5 minutes to remind you a little bit about vectors. Most of you should know them, I imagine, but I need to crash, 5 minutes crash course in vectors because we will be using them the whole semester. And that's basically the only thing I need from you in terms of mathematical knowledge in this course. So let us remember very well that vectors are used to represent quantity that have magnitude and direction. And if you have a vector, this point here is usually called the tail, and that's the head of the vector. And suppose I call A the tail and I call B the head. So the way we will denote a vector is, when I am teaching it, I will denote it with an arrow. The book does not use the arrow. The book uses bold letters, something like that. But this is for me very tedious to do on the board. So I use arrow to denote a vector. So vector is nothing more than a physical quantity that represent something that have magnitude and direction, like force, like velocity, like acceleration, okay? Now we add vectors, as you know, and we scale them. So let us remember how we add vectors. So suppose I have a vector, let's say u, and I have another vector that's a v. Okay, so how we add them? We, as you know, we have two ways, either tail to head or parallelogram rule. Either one will give me the same. So we take the vector u, and from here we're gonna take a line parallel to v. That's it there. And this is what we call the u plus v. So that's how we add them geometrically. And parallelogram rule, so either one will definitely get me to the same thing. Parallelogram rule go like this. This is my vector u, and this is my vector v. You construct a parallelogram that have for side u and v, basically. And then you connect to the vertex right there. All right, so that's how we add geometrically. And then we scale vectors. So if I have a vector u, then geometrically we scale. So we talk about c times u, which is a new vector, of course. How is it obtained? So this is u. C times u is obtained from u by stretching by a factor of c. So if c is positive, and then c negative. So this is my vector cu. So we stretch by a factor of c, if c is positive. If c is negative, we also stretch, but in the opposite direction. So this is my u here. C times u, if c is negative, it's the same thing, but we go in the opposite direction. So we stretch it in the opposite direction, c negative, all right? So most of us, imagine, are familiar with how to add them geometrically and how to scale them. Right? And when I move the paper, please let me know if you guys are okay with it or you want me to keep it. Right. Now, part 2 is, we talk also about the component of a vector in a plane. So we talk about that a little bit also. So component of a vector in a plane. So component. Of a vector in a plane. We're gonna put vectors in a plane for now. We're gonna put vectors in the XY plane right here. Okay, and we are talking about the component. Now, first, the main thing is that vectors have tails and head. And in physics, the tail and head could be basically everywhere you want. In this class, in linear algebra, the only thing I want, and that's important for me, in here, all the vectors in my course, in linear algebra, all the vectors have their tails at the origin. Have their tails at the origin. Okay, so whenever I'm drawing a vector, I'm always started at the origin. That's about the only requirement I want. Now, with this in mind, suppose I have a vector. So if I'm starting at the origin and I take any point P here, x1, x2, now I can construct the vector OP. That's my vector OP. So the point P has coordinates, you can call them xy and x1, x2. So suppose this is x1, x2. And when we are giving names to the axis, usually the horizontal axis is the x1 axis and this is the x2 axis. That's how it is. And then in R3, we talk about x1, x2, x3, and so on and so forth. So first, all my vectors have their tail at the origin. So what are the components of the vector OP? If the tail is at origin and P is the head of it, then the component of the vector OP are the following. Nothing more than the horizontal displacement from 0 to the point P and the vertical displacement. So the component, and we're going to write them this way, so I'm going to use matrix notation for them, is nothing more than x1, x2. So this is what we mean by the component of the vector OP. Okay, it actually makes sense. So the point P basically have coordinate x1, x2, and those coordinates are the component of the vector OP. And there is no ambiguity in our class because they all start at the origin. So for example, if I tell you the following, if I tell you draw the vector, whatever, -1, -1, 2. That's the notation I use. Now, other classes use different notation for vector. They use this. In our class, we're going to need to know them like matrices because it's important for us. All right, so draw the vector -1, 2. We all will draw the same vector. There is no ambiguity for us because we all start at the origin. So I take the point -1, 2, and this is the vector -1, 2. Okay. Now, the last thing I would like to mention is we added vector geometrically. And if I have two vectors and if I know their component, and if I add them geometrically, I get a new vector. What's the component of the new vector? So component of the sum of two vectors. So component of the sum of two vectors. Of the sum of two vectors. Okay, so this means the following. You have two vectors, u, that it is u1, u2. Okay, and v, which is v1, v2. Okay, so we add them. So we're creating, when we add them, we create a whole new vector. And the question is, geometrically, what's the component of this new vector? So when we create them, what do we get? So I will not put anything here. I will go back to the picture and remember what it is. So now I have here two vectors. The first one is u. Remember, for me, a vector is totally determined by the coordinate of this point. So this is u1, u2. And then I have another one. Let's say this is v. And v is denoted totally v1, v2. I will add them. I will add them geometrically, head to tail. It means from the head here, I draw a vector totally parallel to v, right there, and that's the sum. Okay, another question is, what is the coordinate of that? The coordinate is nothing more what's the component of the vector u plus v. But the component is nothing more than the coordinate. What should go here and what should go here? Okay, now a bit of geometry actually tells me the following. So I want this. Basically, I want this one. So let us watch a little bit how easily we can figure it out. Okay. From here to here, that's u1, because that's the coordinate of the component of the vector u. So this is u1. From here to here, u1. How much do we have from here to here? Remember, this vector here is parallel to v. So from here to here, I actually have v1. So this point down here is u1 plus v1, which is the coordinate of this point. Okay, I can do the same idea. And the second component is going to be u2 plus v2. So the geometry tells me exactly what the sum is. So if I take two vectors, add them geometrically the way we added them, we create a third vector. The third vector will have very easily, and it's actually very interesting that this new vector will have for component this one. That's the u and v. Okay. Now the last thing is that, what if I take a vector and scale it? C times u. So you're creating, so my vector has for component u1, u2. So you create another vector, and we know how to scale. So suppose this is the idea. This is my vector u, and it has for component u1, u2. You take it and you scale it. Right there. You're creating a whole new vector when you're scaling it, a whole new vector. Then the question is, what's the component of the new vector you're creating? Again, we use a little bit of the geometry. So I want the coordinate of that point, because geometrically, that's how we scale. Again, we use geometry. So if this is C times U, and I think a little bit in terms of similar triangle, if this is U1, if this side is stretched by a factor of C, it means this side will have to be stretched by a factor of C as well. So that will be CU1. And the same here. If we stretch this by a factor of C, this side will be stretched by a factor of C. So my new vector will have for component CU1 and CU2. Okay, so that's the part of vectors that most of you are familiar with. So geometrically, we know how to add them. Analytically, it means when we start assigning component, we can add them. And the new vector we add have very nice component. It's the sum of the component of the u's and v's. When I scale it, I create a new one. This new one have very nice component, which is CU1 and CU2. Okay, so this is the part of vectors that I think most of you are familiar with. Now we going to introduce our vectors, all right, which are exactly the same. So we're gonna talk about Rn. What is Rn? N in integer, positive integer. Okay. We're gonna talk about vectors in Rn. All right, so first I start with R. What is R? R is nothing more than all the real numbers, pure and simple. So R is nothing more than the collection of all real numbers, nothing deeper than that. Real numbers. Okay. Now, what is R? R, what we call 2, with 2 in the top. Okay, what is R2? R2 is nothing more than the collection, this is a collection of all ordered pair of numbers. So not one, it's an ordered pair. Ordered pair of numbers. So when we think R2, it means a collection of all ordered pairs of numbers. Now, how do we write those numbers? So we can denote them by the notation you want. Then I will tweak it. So one way, ordered pair, I can denote them x1, comma, x2, nothing more. That's an ordered pair, which represent the points in the plane. However, there is another way we can denote an ordered pair that we will be using in this class more. We're going to denote them, or more often, we denote them as 2 by 1 matrix. We want to see them as matrices, or more often denoted by, so it's a pair, but instead of putting a bracket and a comma in between, so we're going to denote them by as a 2 by 1 matrix. It means what? 2 by 1 matrix. It means matrix, 2 rows, 1 column. So we're going to denote them this way. It's important for us to see them as actually matrices, or the vector notation I introduced a minute ago. All right, and we call them vectors, and they are called vectors. So when I say a vector in R2, what do I mean by that? Nothing more than an ordered pair of numbers. That's what it is. It's not one number, so 2 is not in R2. When I say R2, it means I'm talking about ordered pair. 1, 2, 4, 6. That's what I'm talking about. I do all type of ordered pair. And the way we write them is as a 2 by 1 matrix. That's how we're going to write them. And sometimes we write them like this. Most of the time, we will be use this notation for them. And the way we visualize them is the way you expect me to visualize them. The way I'm going to visualize them is, suppose 1, 2. The way I visualize it, I take 1, I take 2. So that's 1, 2. That's 1, 2. And sometimes, because we will add those, we visualize them as a vector starting from the origin all the way to 1. Okay. Now, by the same ideas, we like to generalize, because in linear algebra, we generalize everything, you know. So what is R3 is going to be? It's the same thing, but instead of having ordered pair, we're going to have triple. So all, we say all triple. Actually, I don't like triple. All list of 3 numbers. Okay, just 3 numbers. The ordered list, so all ordered list, that's better. All ordered list of 3 numbers. So, and we can either write them x1, x2, x3, or at the 3 by 1 matrix, which I'm trying to emphasize a lot. x1, x2, x3. Okay, so R3, when I tell you a vector in R3, you just think of a 3 by 1 matrix. Nothing more, nothing less than that. And because we need to visualize things in this course, so if you have, for example, 1, 2, 3, how we visualize it? Okay, we take, that's in 3 dimensions, x1, x2, x3, and the way, this is usually my x1, my x2, my x3, and the way I visualize, it's 1 in the x1 direction, 2 in the x2 direction, and 3 in, so it's going to be this vector right there. So that's really my vector. And now the most general idea is Rn. So what is Rn? Can you stretch a little bit the definition? That's going to be my definition of Rn, not my definition, the definition. Anybody? If I have Rn, and it's any integer, it's going to be defined as follows. It's going to be defined as the collection of all ordered list of n numbers. Ordered, it means the order we put the numbers is important. So Rn is going to be the collection of all ordered list of n number that we gonna denote either sometime between bracket x1, x2, etc. to xn, or as an n by 1 matrix, which is x1, x2, all the way to xn. So Rn is nothing more than the collection of all ordered list of numbers that we're going to write them this way. Are we going to be able to imagine them? No, we only imagine them for R, R2, and R3. After that, we just accept them. Now, have we seen so far a, so vectors in Rn, it means something that have n component. So if I tell you, give me a vector in R5 is nothing more than a 5 by 1 matrix. That's really what I mean. 1, 2, 3, 4, 5. That's a vector in R5. Or you can put anything, square root of 2, e, pi, 5. So just a collection of 5 numbers. Now, have we seen any list of 5 numbers? If I take a system that have 5 unknowns, the solution consists of 5 numbers. So we're going to start seeing the solution of a system with 5 unknowns as actually a vector in R5. Okay, so now we're going to start seeing solution as vectors, and we're going to switch writing solution as list of numbers. We can actually start eventually, very soon, we're going to start writing them as vectors, not only as a list. All right, so they will come up all the time with us as solutions of system. That's we use the vector in R5 in our class. Now, algebraic operation on Rn. So we add vectors in Rn and we scale them. So algebraic operations on Rn. Okay. So this tells me that if you have two vectors in Rn, suppose u and v, so we're going to call them u1, un, n component, and v1 through vn. The same number component are in Rn. Now we add vectors in Rn, and our operation are totally inspired. So those are definitions now. Inspired by what happened in the plane. So I have a vector u, so that's my definition. What does it mean to add vectors in Rn? un, v1 through vn, adding them will create a third vectors. And u plus v is obtained. We want our intuition to guide us. If I have vector in R2 and I add them geometrically, the new vector has for component u1 plus v1. I want to generalize this idea. So u plus v is going to be the vector u1 plus v1, u2 plus v2, etc., un plus vn. So we add vectors in R5, R16. It doesn't matter how many entries we have. We add them the same way we add the geometric vectors. Again, we will talk about scaling a vector. So C times U. So this will C times U1 through UN, and that's a new vector. And the component of this new vector is C U1, C U2, C UN. So scaling a vector will create a new one that has for component CU1. Again, our definition is based on what happened in the planes. That's how the generalization is based on that. Now, to comment. First, we cannot add vectors that do not have the same number of components. It means we cannot add a vector in R5 to a vector in R2. This doesn't really make sense. We only add vectors that have the same number of components. Okay, so something like that is absolutely nonsense. So we add vectors if they have the same number of components. So if a student supposedly write the following, 2, 3 plus 2, 3, 5, that's absolutely nonsense. So we only add vectors if they have the same number of entries. 2, what does it mean for two vectors to be equal? Two vectors are equal if, first, they have the same number of entries. So I cannot compare vector in R2 to a vector in R3. So they have the same number of entries, and they have the exact same entries. So to compare two vectors, those vectors cannot be, they have to have the same number of entries. So if a student writes something like that, x1, x2 equal, 1, 0, 2, this absolute nonsense. Equality hold only for vectors that have the same number of entries. Okay. All right, now I'm going to introduce a new word and a new idea, not hard at all. It's called idea of linear combination. So the first main definition today is the notion of linear combination. I put the definition in front of us, and then we start working with it. So let me put it up, and then I'll work. Okay. Linear combination. Okay, so that's the definition. So suppose I have vectors v1 through vk. It means k vectors. Vectors in Rn. It means I have k vectors. All of them are in Rn. What's a linear combination of vectors? What's a linear combination? A linear combination of v1 through v1 is just any vector that's obtained in the following way. So it's v1 plus v2 plus vk, but we put a certain weight on each one of them. So it's a vector which is c1 v1 plus c2 v2 plus c3 v3 plus ck vk, where the c1, the ck's are scalars that we call them the weight of the linear combination. So if you have a bunch of vectors, a linear combination of them is nothing more than you take those vectors, you put weight on them. It means you scale them, you scale them, you scale them, and then you add them. That's what's a linear combination. So let us take a fairly straightforward example. So example, suppose I am in R2 because it's simple to work in R2. So let me take the following vector. Suppose U is the vector 2, 1. So I am in R2. And V the vector minus 2, 2, for example. So I am in R2. Okay. Now let us form some combination of U and V. So let us form some combination of U and V. So what's a combination? What's a linear combination of U and V? It's nothing more than you stretch a little bit U by a factor, you add it to another stretch of V by some other factor. So let us give two linear combinations. One linear combination is, for example, 2U, so we set this by U, plus V. That's a linear combination of U and V. Okay. In this scenario, my weight, C1 is 2, and C2 is 1. These are the weight. And geometrically, what is 2U plus V? So geometrically, it means the following. What's a linear combination? So you have the vector 2, 1, 2, 1. That's my U. That's my U. Right there. My V is minus 2, 2. Minus 2, 2. Okay, that's minus 2, 2. Okay, so these are my main vector. That's my U, and that's my V. What's a linear combination? Linear combination is, you take the vector U, you stretch it by a little bit. So we stretch it by a factor of 2. And then what do you do with it? You just add V, you take from. So you move a little bit in the direction of U, then tiny bit in the direction of V. You get somewhere here. This resulting vector, that's a linear combination. So the linear combination are vectors that you get by stretching U a little bit, and you add to it some kind of a stretch for V. And that's really what we call a linear combination. That's the 2U plus V. Now we can make a lot of linear combinations. Who can give me another one? Who can give me another linear combination? So that's one combination of the two vectors. Who can give me another combination? That's the matter of, putting scalars next to the vectors. 3U plus 2V, that's another linear combination. 3U plus 2V. And they can be negative. I mean, they don't have to be positive. Let's get that straight. The scales don't have to be positive. So in this scenario, he put a weight of 3. So those scalars, we call them weight because how much we're weighing those. And the other one is a 2. Okay, these are the scalars he gave. So now we can, so if I want to draw this, so it's not really hard. This is my U. It means he wants me to go, let me pick the purple. I don't want to use another color, another picture. So he wants start here. We go 3 units in the direction of U. That's what we're doing. And then we'll add to that 2 in the direction of V. 1, 2. And then the resulting vector, that's a linear combination. So linear combination, at least for 2 vectors, are those vectors that we can get by stretching a little, moving a little bit in the direction of U, and then moving a little bit in the direction of V, and then the resulting is what we call the linear combination. So we can form infinitely many linear combination of a vector, of 2 vectors. So let me tell you this one, 0U plus 0V. which is basically the 0 vector. That's a linear combination. And my linear combination here are C1 is 0, C2 is 0. So this here is considered also a linear combination. All right? Now the second question is the following. Suppose I pick a vector. Let me pick the vector 1, 5. Any vector different from U and V. 1, 5. And the question is B a linear combination? What do I mean by that? Is B a linear combination of U and V? So I pick an arbitrary vector and I'm switching a little bit the question. Is this vector I created a linear combination? What do I mean by that? What do I mean by that? I mean that, is it possible to take the vector B? Is it possible? And write it as a scalar times U plus a scalar times V? That's what it means. So if I pick a vector and ask you, is it a linear combination? It means that, is it possible to write it C1U plus C2V? So let me introduce, I'm gonna go back to this question, of course, but so let us see, I'm trying to write this as a definition. So suppose I have a bunch of vectors in Rn and B another vector in Rn. All my definition in this class will be in the general setting. And then we took examples in a simple setting. We say that B is a linear combination of those. So I have a bunch of vectors. We say that B is a linear combination. If I can find scalars or weight, C1, C2, all the way to CP, such that when I put weight on those vectors and I add them, I can hit the vector B. So B is a linear combination if there is possibility to find those weights that will give me B. It means it's possible to stretch V1, V2, V3 and add them so I get B. Okay, let's do this problem clearly. So we're going to do this problem purely algebraically first and then a little bit geometrically later on. So this is my question now that I've asked a minute ago. Suppose U is this, and this is V, and this is B. The question is, show that B is a linear combination of U and V. Let us understand clearly what it means. It means show that it is a linear combination. So my question now is the following. Find weight C1 and C2. That's really my question is. Such that C1 U, so I want to find those weight so that when I do this, I get the vector B. So show that B is a linear combination. It means give me the weight that I should put on U and V so that this will give me the vector B. So by stretching U and stretching V, I actually hit the vector B. All right, how we do that? Algebraically, purely algebraically. Now this type of equation, we give it a name, and that's what the title of the section is. This is called a vector equation. What the vector equation coming from? Equation means equality between objects. Vectors is because we have inequality between vectors. That's really what it means. So let us find that. Let's find the C1 and C2. All right. Okay, it means we need to find C1 such that U is 2, 1. Once we understand the algebra, and V is minus 2, 2. So we're gonna find C1 such that this will give me 1, 5. That's really what I am after. So I'm after the C1 and the C2. Those really are my unknowns. All right, so what does this mean? What does it mean to multiply vectors by a scalar? So it means that 2C1, C1, so the coefficient here are the C1s. So the coefficient of C1 are the entries of U, and this one, minus 2, 2, equal 1, 5. I'm after, sorry, I want minus C2 and C2, my apology, 1, 5. I am after those scalars. I'm after those C1 and C2. So this means that, so that's a vector, I'm adding another vector to it. So it means I need to find the weight, those are my unknown, so that this is 1, and my unknown. So this is A5. Okay. All right, please, if you have any question, let me know. All right, so what does this mean? Watch carefully what this means. I want to find the C1, C2 so that this vector will be equal to this vector. But how two vectors are equal? They are equal if this component equal to this component, and this component is equal to that. It means I need to find C1, C2 such that 2C1 minus 2C2 equal to 1, and C1 plus 2C2 equal to 5. So the question now is we need to find C1 and C2. So finding those weights really boils down to solving the system. Now this is an easy system. I know you can spot it and solve it, but I'm going to solve it the way we've been solving system in class. So finding C1 and C2 really boils down to solve the system. So let us write the augmented matrix that correspond to the system and a little bit analyze it. What's the augmented matrix? 2, 1, and minus 2, 2, 1, and 5. So that's the augmented matrix. Now, if we watch very, very carefully, what the 2 ones were, this is where the C1 came. It's nothing more than actually the vector u. So in the augmented matrix, the first column is nothing more than the vector u. And in the augmented matrix, this is really nothing more than the vector v. So it's actually a good observation. And the augmented term is nothing more than the vector b. Okay. So let us solve this system. Now, how do we solve it? As I mentioned at the beginning, I don't want to work with 2. I'm going to switch rows. So I will have 1, which makes life a little bit easy for us. And that's 2 minus 2, 1. I only do that because working with 1 is easier than fraction. And now I multiply the first row by 2, add it to the second row, and this would be my second row. And this would give me a 1, a 2, a 5, minus 2 plus 2, it's a 0, minus 2, minus 2, minus 6. So if I do any mistake, it's your responsibilities. And then here I will have what? Minus 10 plus 1, minus 9. All right? Now you can go further if you want, but it's a simple problem. I don't want really to go further. So I have a leading here. Remember, my unknown are the C1 and C2, and I have a leading here. And I have consistent system. There is no problem with the consistency. Okay, I don't have any free variable in this problem because I have leading in every column. Every variable is basic. So we just write the system and solve. So the second row, we read minus 6 C2 equal minus 9. So this would give me my C2 equal, if I divide by 6, equal to 3/2. A little bit of math. And now the first row would read C1 plus 2C2 equal to 5. So let us solve. So C2 is 3/2, and the first one gives me C1 is 5 minus 2C2. That's 3/2, and 2 and 2, 5 minus 3, which is give me a 2. So what does this mean to us? This means that the vector B can be written as 2 times the vector u. She could be iterated plus 3/2 the vector b. So my vector is actually a linear combination of the 2 vectors u and v. And now I can check actually. So let us check. Let us check. Let us check. If I take 2u plus 3/2v, it means if I stretch 2 by 2 unit, v by 3/2, do I actually hit the vector b? All right, so let me see. 2 was 2, 1, and v was 1, 5. So if I add them, what will I have? 4. No, sorry, that's 2. That's minus 2, 2. I was wondering. I want to reach 1, 5. Okay, that's going to give me 4. And minus 2 and 2 cancel out. 4 minus 3, that's give me, of course, a 1. And that's give me a 2, 2 plus 3, which is give me a 5. So I'm definitely doing fine. Okay, so is B a linear combination? Yes, it is. If I stretch U by 2, V by 3/2, we hit the vector B. Any question before I go on? Let us understand this problem a bit geometrically, because it's a simple problem that I can actually explain geometrically before I do cases where the geometry is actually not very easy. So, okay, let's see what the problem here in this simple scenario for the simple vectors U and V. So I have my vector U to be, I pick my vector U to be 2, 1. And my vector V is -2 and 2. Okay, I'm going to draw them here. Try to be accurate. So my U is 2, 1. So now I'm doing the problem geometrically. We did it algebraically. Now I'm going to explain a little bit the geometry of it. So that's 2, 1. So this is my U. Okay. V is -2, 2. -2, 2. This is my vector V. So, okay, let me try to be a little bit exact for once. So that's my vector V. UV. Okay. And then my vector B is 1, 5. Okay, so I'm going to draw my vector B. So it's a 1, 1, 2, 3, 4, 5. Go like that. Okay, and this is B. That's my vector B. Okay, now I'm trying to explain geometrically the picture. My question was, and we answered positively algebraically, can you stretch U by a little bit and stretch V by a little bit to get the vector B? So how can you think about that yourself? You think the easy way to think about yourself is the following geometrically. This is my U. Imagine you have 2 lines, one that carry U, that's U, and another one that carries the vector V. So think of 2 roads on a street. That's the easiest way to think about it. And then you ask yourself, if I want to go from 0 to B, can I go from 0 to B following the direction of U and V only? That's my question to you. Can I go from here to here by following only the direction of U and the direction of V? So I cannot wiggle. What do you think? Pure geometry. So imagine you have 2 roads. You want to get here. Can you go only in the direction of U and direction of V to get to the point B? Absolutely. Yes, because I think about it. This is U, so I'm going to go like this. So this is my V parallel. So I'm going to start moving to get B. Parallel to V, a little bit more, a little bit more, a little bit more, a little bit more, right there. Okay, so I'm going to go up to here, almost. I mean, my picture. And then, so I go here, and then I go parallel to V. So I go this way, so my picture is a little bit off, plus that way in the direction of B, and I can hit the vector B. And that's really what we are doing. What we are doing is that can you put a little bit on U, a weight, and move a little bit in the direction of U, a little bit in the direction of V, and hit the vector B. And the answer geometrically for this particular problem is actually even algebraically was yes, and geometrically it's also yes. So let me take, before I move to R3, let me take, for example, a vector here. I'm going to ask you the same questions. Let me call this as a W. Okay? Do you think I can write W as a combination of U and V? It means, can I move a little bit in the direction of U and then move in direction of V to hit W? What do you think? Geometrically, not algebraically this time, because I did not even give you component. Any idea? So can I move a little bit in direction of U? A little bit, then in the direction of V, so I can hit here. I mean, Matteo is asking me, yes, other student, okay. Yeah, I can go in the opposite direction of V, and then when I feel I can start turning parallel to V, I do it. So let me see something like that. So I'm gonna go all the way here in the direction opposite to you, and then I move right there. Then I'm gonna hit my vector W. Okay, so geometrically can you write as a combination of U and V? Geometrically means, can you go to the vector W by following the two direction of U and V? So for those vectors I gave you, the answer is geometrically intuitive and algebraically we did it algebraically, right? Now let us take another example where I go to R3, where our geometry is a little bit not as simple. So example number 2. Okay, here's my problem. I'm in R3, but everything generalized. So I have the vector V1, 1, 2, 3, V2, 4, 5, 6, V3, 5, 7, 9, and this is my vector B. And now my question is, that's purely algebraically, so we understand the algebra. Is B a linear combination? It means, what does it mean? It means, can I find C1, C2, C3? So is it, it means, can we find weight? C1, C2, and C3, because I have 3 vectors, such that. That's really my question. If I stretch V1 by a little bit, then I stretch V2 by a little bit, then I stretch V3 by a little bit, I hit the vector B. So finding if B is a linear combination is really boiling down to solve this equation that we call vector equation. Okay, but what does it mean to solve this vector equation? So it means I'm looking for that 1, 2, 3 plus C2, 4, 5, 6 plus C3, 5, 7, 9 equal to minus 1, 1. And means I'm solving this vector equation. Now, I mean, we don't know any solution. I mean, we look at it, this is really, I mean, it's hard to tell. Sometimes it's easy to tell, but now it's hard. But this is equivalent to solve what? I'm gonna add, those are 3 vectors which are weighted. I'm gonna add them. I get C1 from here, and I get 4C2 from here, and I get 5C3. And then I will have 2C1 plus 5C2 plus 7C3, and here I will have 3C1 plus 6C2 plus 9C3. And this should be equal to that. So now my question is, can I find those weights, C1, C2, and so on? All right, so let's see if we can do that. So this is really equivalent to solve the following system. So solving this vector equation is really equivalent to solve the following system. 1, 3C1 plus 6C2 plus 9C3 equal to 1. So solving this is boiling down to solve a system where the unknown in this particular problem are the weight of the linear combination. Now, everything we do in this class is going to boil down to solving a system. That's why we start by that. Okay, but every time we have to know what are we solving for? What are the unknowns in the system are? In this problem now, the unknown are the weight. So let us solve the system the way we know how to solve the system. So immediately we're going to take the augmented matrix and reduce it and hopefully get the answer. So the augmented, and again, I will make a comment on the augmented as I made before, but by now I think you guys know what the comment is. So 1, 4, 5, minus 1, that's the 2. And that's a 2, and the 5, and the 7, and the 1, and the 3, and the 6, and the 9, and the 1. Okay, so before we go on, let us see what kind of augmented we're getting. The augmented will be getting, so basically the coefficients of C1 are coming from the vector V1. That's why we're ending up with the vector V1 in here. The coefficient of C2 are coming from the vector V2. This is the vector v3. That's what we already did before. And finally, this is the vector b. Okay, and now the question is, we have to take this augmented, reduce it, and see, is it possible to write that? So let's do that. Okay, please, if I pull papers ahead of time, let me know. So let us row reduce this matrix, because I don't know. This is a mess of a matrix. It's not easy to look at. So we do operation. So I have my 1. It's not sitting nicely here. I don't touch it then. And then minus 2 plus 2, it's a 0. Minus 8 plus 5, right? So this is minus 2 plus 2. That's minus 8 plus 5. Give me a minus 3. Minus 10 plus 7. Minus 10 plus 7. That's a minus 3. Trying not to do a mistake. I don't promise. And then I will have here minus 2, which is 2. 2 plus 1, it is a 3. All right. And then I have to watch. I do 2 operations at once because it's easier. So the first operation I'm doing twice the first plus the second into the second. And the second operation I'm doing is 3 times the first. So I'm not touching the first. I'm using it to create a 0 and a 0. So I'm not really touching that first at all. That's what I am doing. So minus 3 plus 3, it's a 0. Minus 12 plus 6, that's a minus 6. Minus 15 plus 9, that's a minus 6 also. And 3 plus 1, that's a 4. So I have now, I move, I create a leading here, which is minus 3, and I make under it 0. So this will give me the following. 1, 4, 5, minus 1. So to make this into what's under it into a 0, I need to multiply the second row by 2, add it to the third, and this will create my third row. And this will give me a 0, minus 3, a 3. Okay, 0, that's a 0. Minus 2, it gives me a 6. Minus 6, it's a 0. Of course, it's a 0. And then here I have minus 2 times 3, that's minus 6. Minus 6 plus 4, it is a minus 2. Okay, so what does this mean in this scenario? So I try to find those weights, and I realize that I get that. Now, what kind of system this is? Absolutely, that's an inconsistent system. The system is inconsistent. Means the system does not have a solution. What does this mean for us in this particular context? What does it mean? We go back and we try to see what were we looking for. We're looking for weight. C1, C2, C2, C1, C2, C3. So as we stretch them, we can reach the vector B. If the system is inconsistent, it means this vector, there is no way I can put weight on the scalars so that we hit the vector B. So conclusion in this particular problem is that the vector B is not a linear combination. Is not a linear combination of V1, V2, and V3. So there is no way I can reach the vector B by following the direction of my vectors V1 and V2. So this is my vector 1, 2, 3, 4, 5, 6, and 5, 7, 9. Those were my vectors. So that's my V1, and that's my V2 and my V3. And this was my vector B, 1, 1, 1. And what we showed that there is no way I can combine those, they're linear, and get the vector B, which is sitting like that. Okay. Of course, we have to understand a little bit the geometry. Today I start a little bit the geometry, and we keep talking about it throughout the whole semester. What's the geometry in this picture? What's the geometry? This is a vector V1 has 3 components. So this vector, so I'm start giving you a glimpse of the geometry. That's the vector v1, assuming this is the vector. So I am in R3. And that's the vector v3. Sorry, v2. Okay, and watch how I pick the vector v3. 1 plus 4 is 5. 2 plus 5 is 7. 3 plus 6 is 9. So I really picked a vector v3, which is nothing more than the sum of those two. So if this is v1, this is v2, my vector v3 is somewhere in here. Okay. Now, the vector b is not a linear combination. What's geometrically, the way we're gonna basically explain it is the following. As I said, I start giving you a glimpse of what's really the situation here. If I take the plane, the following plane that contain 0, that contain v1 and v2, so that contain those 3 points, this is a plane in R3. What's happening is that this vector b is living outside the plane. So there is no way that you can reach this vector you following the direction of v1, v2, and v3. That's the geometry that we're gonna slowly develop in those ideas, okay? So let me a little bit summarize a little bit. Not summarize, basically terminology, because as you know, this book has a lot of terminology. First, when we're trying to show that B is a linear combination, we have to solve an equation like that for the weight. It means we ask ourselves, can we find those scalars to give me B? This type of equation is called a vector equation because inequality between vectors. Now, solving this equation. So when we try to solve this equation, solving this equation really boiled down to solve the system that has for augmented matrix v1, v2, v3, vk, and the augmented term. The solution of this system, so once I solve it, if it's consistent, so when we solve the system, the solutions are the weight that will give B as a linear combination. All right, so that's a little bit of a summary. Showing that B is a linear combination really boils down to solve the system. This is called vector equation. This is the augmented matrix that correspond to that system. And the solutions of this augmented have a meaning, very particular meaning. They are those weights that will give B as a linear combination. So when we solve that, we're actually looking for the weight that will put on those V's to get B. If we don't get solution, it means there is no way we can put weight on that. Okay, so that's the main idea for today. So it was the idea linear combination, which is really simple. What we will be doing next time is the idea of what we will call the span, which is idea fairly simple, not simple. I mean, it's the idea is the following. If I have two vectors, like the one in R2, for example, the one I've been playing with, so the vector U1 and V, which was the vector minus 2, 2. And as we said, we can form a lot of linear combination, infinitely many. You know, we can fit 2U plus V, infinitely many, infinitely many. So since I can form a lot of them, the question is, what if I take the collection of every possible linear combination? What do I get? So I take every possible linear combination of those two vectors, and we're gonna give them a name. And we're gonna call them the span of those two vectors. And we're gonna ask ourselves, you know, if I take every possible, what do I get? Okay, can anybody give me, for this particular question, anybody has any intuition what the answer is? Anybody, any intuition? If I take this problem here, take it to the picture, that's my vector U, which is 2, 1. That's my vector B. If I start taking every possible linear combination of those, what do you think we may get? Do we get everything in R2? Can we get every vector in R2? So I was able to get that vector. I was able to get that vector. Suppose I pick a vector here. Can I write this as a combination of my vector 1, 2, and minus 2, 2? What do you think? Can I get from here to here by following those two directions? That's my U and that's my V. Is it possible to get there? All right, everybody, again, with telling me I can start from here. I can go a little bit in the direction of minus U, and at some point I need to get back in the direction of V. Imagine yourself driving and you start asking yourself, okay, if I go parallel, I won't get. I move a little bit. Do I go parallel? No, I cannot get. I move a little bit. Do I go parallel? I hit. So I can really get there. And I can do that if anywhere my vector is. So intuitively, when I'm going to take every possible combination of those two vectors, I'm hitting everything in the plane. So it means basically, we will say next time that the span of those two particular vector is going to be everything in R2, meaning every ordered pair of numbers. Actually, I can write it as a combination of those two specific ordered pairs. Okay, you can get it. That's a different question. And slowly, we will reach. Can you get every vector in Rn? Yes, we can, but we need at least n vectors that have specific properties to be able to get every vector in Rn. And that's what will be the subject of part of our course. Okay? Any questions before we go? Please do the homework. I will assign for the third time questions from section 1.2 because it's crucial for us, and I will assign you homework. So please do the homework, and your quiz will be next Wednesday, as you know. Okay, bye for now. If you have any questions, stop by my office hours. Bye-bye. If anybody wants any question, personal question, you guys can hang around.